Hello everyone and welcome to another Motec webinar. My name is Mark McCoy and I'll be your host for this webinar. Today's subject is some basics on tuning PID control loops. Hopefully everyone will have watched my PID parameters explained webinar previously, just to give the background of these parameters that we're going to be tuning today. This is a basic webinar. There's actually a fair bit more in tuning PID than I can obviously go through in a short webinar, but this will give you the basics of what you're looking for, and at the end I'll give you some helpful hints on a few things that seem to be common questions. The subjects I will be going through today are feed forward, system linearity, step aim change, the proportional derivative and integral gains, that'll be more the tuning, dead bands, and some helpful hints. To get started, the first thing we need to consider is the feed forward. Now, my last little point there is over the years the software guys have called this feed forward or the feed forward table a couple of different things. So you might see in earlier versions of software there'd be something called a normal position table or an average position table. That's the same thing, it's all feed forward. So generally all the PID functions will have a feed forward. The idea of feed forward is if we have for boost control we've got a duty cycle, so ultimately we're sending a duty cycle to the boost control valve to give us the boost we require. Or if we've got drive-by-wire throttle as idle control, we've got a position that we know will give us about the right idle. So what we're doing is trying to find what is the best duty cycle or position which is going to give us our answer pretty much straight off, without having to do any PID. So it's more or less the closest answer, duty cycle or position, that will give us our aim. So basically no error without even having to do any PID tuning to start with. So this is effectively an open loop system. So to get a closed loop system, a PID system, working, you first need to understand how the system works in open loop. So either the boost control or the idle control, maybe even the cam position sort of tuning. My advice to you is the feed forward table or values are extremely important to the PID system. Basically, if you give it the system a very close answer to begin with, it means that the PID, the closed loop part of the system, has to do a smaller amount of work. Now if it has to do a smaller amount of work, trust me, it makes your job as a tuner much easier. So feed forward, extremely important. As a couple of examples, I'll give you the first one here for boost control and another one sort of for idle control. So this is just sort of an idea of to give you an idea of what you're going to be doing as a process. If we have a boost control system and we ultimately want to have this as a closed loop PID system, the first thing we are going to do on the dyno is just simply run the boost control as an open loop system. So PI and D will all be turned off, and as you can see here, the diagram down the bottom, I've got my normal position table for my boost control. Now what I would do is maybe first off you might just have one axis of RPM, so we're just going to look at boost control based on RPM. So you would go into this table and on the dyno you would adjust the duty cycle of this valve until you got the boost that you wanted. So if you wanted 1 bar of boost, you would adjust the duty cycle for each RPM site in your table until you get the 1 bar. So no PID, this is purely open loop. We're finding what is the feed forward or the duty cycle that will give us the boost we want to start with. Now, as you can see in my diagram, I've also added throttle position. So, what we try to do with especially highly boosted engines these days is the drivability becomes extremely important. So what we're doing is we're saying, okay, we want different amounts of boost at different throttle positions and different RPMs. So, what we're doing is we're finding the base duty cycle, which will pretty much give us that answer to start with. So you do all this work either on the dyno or, if you're careful, on the street to start with. This part, the more accurate this table is, again, the better your PID control loop will be, and also the easier it will be to tune that PID control loop. So again, very important to get this right first. For idle control, for an example, if we had duty cycle or drive-by-wire position, what we would be doing in the idle normal position table is we would be finding what is the duty cycle or position that pretty much gives us the idle RPM level that we want to begin with. Again, no PID, no closed loop. This is an open loop test. So you can see my table down there is a fairly typical what would be a duty cycle valve for idle control, and it's based on engine temperature, because generally speaking, when the engine's cold, you have an extra 100-200 RPM of idle RPM. So what we're doing is we're saying, this is the duty cycle curve based on engine temperature that's going to give us our aim idle, fairly close to start with. Just a note there that for a stepper motor idle control, there is no feed forward. Okay, so you don't need to really do this test. Another thing, my last point there, is in the idle control we also have an additional air conditioning and power steering feed forward in the list of parameters. So this is basically, if I have this table at the moment at 60 degrees highlighted in blue there, you see there's 25% duty cycle. So that's on the valve to get the idle we want at 60 degrees. But if I press the AC button, there's a parameter to say maybe add another 10% duty cycle on only when the AC is on. And then for the power steering, when the power steering switch comes on, maybe add another 5% duty cycle. So they're all feed forwards. Probably the thing to take from that is, if you have a change in situation, like the boost control before, we did that based on throttle position, not only RPM. If you've got something that's changing, it's always best to try and include that situation in the feed forward rather than try to have the PID sort it all out. An example I had on the phone the other day was the idle control on a boat. Now this boat could either be started in the water, so the propeller would be turning in the the resistance of the water, or they would start it on the trailer, so no water resistance on the propeller. So what I instructed the guy to do is you need some way of working out whether the boat is in the water or not. Now, it sounds like an easy thing to do, but you've got to come up with a sensor for maybe water. But in this case, we used the torque on the drive shaft as an indication as to whether it was in the water or not. So if you can do that, then again, like I said, the feed forward's the most important. The more accurate your feed forward is, the easier the PID system will work and the easier it is to tune. So if you have a situation where it changes the load on the engine for idle control, you should really include it in your feed forward. Very, very good tip, that. Something that a lot of people sort of either forget or ignore possibly. While we are checking this feed forward, this is a good opportunity to check what would be termed our system linearity. This is not a parameter, this is just something you're going to need to test. This is more or less a characteristic of the system that you are tuning. So what we're saying here is, Does each equal step of duty cycle or position produce an equal step reaction? So if we were saying boost control, let's say we put 10% duty cycle in and we get maybe 10 kPa of boost increase. If I put in another 10% duty cycle, do I get another equal step of 10 kPa? So the more linear the system, so every 10% is 10 kPa, if I get a nice linear system, that means the PID will work much better. The basic mathematics of a PID system are designed around a linear system. So if equal steps of duty cycle give you equal steps of reaction, either RPM or boost or whatever, the system will work much nicer. So something especially noticeable on idle control, where you maybe open the butterfly up 1%, might give you, say, 100 RPM, and then the next 1% might only give you 50 RPM. So the linearity is not quite there. That's going to make your idle tuning a little more difficult. The other thing we have to watch out for is what we call the deadband of the device. Now you'll see this mostly in boost control valves, where if we start at 0% duty cycle and we work out what boost we get from 0%, I might put in 10% duty cycle and get the same boost. So that either from 0 to 10% duty cycle makes absolutely no difference to the boost. This means that is like sort of a low-end deadband, 0 to 10%, where the valve physically doesn't do anything. Now this is quite common. So what you might have to find is, what is the minimum duty cycle that makes that valve start doing something? It might be, say, 10, or you might even get up to, say, 20% duty cycle before it does anything. And then from there on you get your linear range, and then once you start getting to the maximum duty cycles of this valve, you might find that the last, say, 10-15% makes no change at all either. So you might get up to, say, 85% duty cycle, and then anything over 85% makes no difference to the boost either. So at this stage, your boost control valve is only going to work between, say, let's say 15% and 85%. So that's what you would set your maximum and minimum duty cycle tables to. So what you're saying is, no matter what the PID system wants to do, don't calculate outside the range of 15 to 85% duty cycle, because those dead bands do nothing, and it's just going to confuse the system, and it's just not going to work. Another example I had a few weeks ago was a car where they were the tuner was reporting that the boost would never get to what they were requesting, and when I had a look at their file, the PID system was actually set up quite well, but what I noticed was when they were getting close to the boost they wanted, the duty cycle was up around 85-90%. Now for the boost control valve, it simply had run out of range, so even though they were requesting more duty cycle, the valve was out of range, it simply wasn't going to work. So in that case, our only option is to change the physical system. We had to put a restrictor in the line to the boost control valve, which more or less dropped or lowered that usable range. So basically, in where it had been using 85-90% duty cycle, it was now down to 70% duty cycle, so well within the linear range of that particular valve. So my point here is that if something doesn't seem to be working, just have an idea of, is it the PID, is it the duty cycle you're requesting, or is it the physical system? Okay. Another thing I've got there is the system too sensitive? Generally with these PID systems, we will also have a frequency as well. So if we're doing a duty cycle controlled boost valve, those valves also work at a specific frequency. Now it's about 16 to 20 hertz usually. If you went up to say 30 hertz, what you would find is that linear range in my diagram would be a lot steeper. So every 10% might suddenly be 20 kPa or 50 kPa. So what happens is, every 10% of duty cycle suddenly gives you a really sharp, really big change in boost. That might not be a good thing. So you might even want to lower the frequency just to spread that linear range out a bit to make the system not so sensitive. So you might find that if you lower the frequency, suddenly 10% duty cycle may only be 5 kPa of boost. It's another thing that you'll find if you have to tune the PID for variable camshafts. The range of duty cycles which they use is very, very narrow. So if you have too much frequency, you'll find that the cam is it reacts so quickly that it's very hard to control, and then suddenly again your PID sort of settings or tuning becomes a lot more difficult. So as a bit of a trick, you can lower the frequency just a little bit to make the system not so sensitive. So again, we are more or less changing the physical reaction, but this time we're doing it in software rather than putting in restrictors and modifying physical bits of the engine. Step change. Now this is a more or less part of the process you're going to go through, so I'm just going to give you a bit of an explanation. A good example here I've used in my diagrams is idle control. You can see I have two traces there. The one in green is the actual RPM, and as you can see in red we've got the idle aim RPM. So ultimately how we're going to tune this idle control is we're going to request an instantaneous step. So you can see there between the two I've gone from 800 to 1200, and you see on the second diagram there's a big step in the red trace, or the aim, or what I'm requesting. So as we tune the P, I and D, because we've already done our feed forward, we are going to be looking for the reaction and how well the actual RPM follows our aim. So this is generally how you would tune a idle control system or even a variable cam control system. You would put an instantaneous step change in the request or the aim position, and you've got to tune to make sure your actual RPM or cam position follows this. With boost control, it can be slightly different. More or less what you're going to do is just bring the engine on to boost and see how quickly the boost control system will achieve the boost you're aiming for. So it's not so much a step response on the boost control. You're just planting your foot on the throttle and seeing how the boost comes up to your aim. For proportional gain, now as I said on my previous webinar, this is a duty cycle or drive-by-wire position, etc. It's a proportional reaction to the error. Now I'll repeat, like, error is what is the difference between my actual RPM in this case and my aim RPM 1200. So you can see the top diagram to the left there. If I start with a little bit of proportional gain, now we're going to tune these in a specific order, so we're going to start with proportional gain. We just put in a small amount. That can depend on the resolution of the proportional term. In various different bits of the software it might be 0 to 1 with 3 decimal places. In other places it might be 0 to 10. So, but just a small amount. We just need a small initial amount just to see what the reaction is like, and then we can adjust from there whether we want to put in more or less. Make sure your integral or your I gain and your derivative, your D gain, are 0 at this stage, only proportional. So what we would do is we would type in a small amount of proportional, then go back into my idle aim table, and in this case I've typed in 1200. Now you can see by the green line in the first diagram, you can see that we've had a reaction, but quite clearly it hasn't gone anywhere near far enough. So we still have a fair amount of error, but we haven't got enough proportional gain in there to get rid of that error. So, simple matter of going to proportional again, adding some more in, and you'll see on the next diagram we get two things. One, our error is much better. We got much closer to where we need to be, and it's a bit sort of difficult to see, but I tried to draw it well enough. You'll see that the reaction, or the rate at which the RPM picked up, is quicker. So your proportional gain will give you a reduction in error, and also the more proportional, you'll get a quicker reaction. Now, without drawing 20 diagrams, I've sort of gone ahead a bit with my last diagram, the third one at the bottom. If you put too much proportional in there, what you'll get is hunting, where you get a really sharp reaction, but it's a little bit too much. So once you go above your 1200 or your aim, the proportional goes, oh, oops, I've got to go back the other way, so it closes. But again, we've got too much proportional, so it closes quickly, and then we drop below, and you get this cyclic hunting up and down of your RPM. So that's obviously no good either. So if I go to my next slide, you can see what we have here is I've tuned it and adjusted my proportional until I get a good reaction, and then you can see that there is a little bit of hunting, so it does go a bit too far, but after a while it will sort of slowly try to settle. I mean, this might have another 2 or 3 overshoots depending on the system, you know, depending on how quickly your engine reacts, light flywheels, etc., all those kind of things. But you're sort of trying to get something that is very responsive, maybe a little bit too much proportional, just enough so that it does have a few hunts, because we want that sharp reaction, but we don't want it continuously hunting. So we've got to find a good common ground where we've got fast reaction, maybe a little bit too much proportional, and it hunts a little bit, but it does steady out after a while. The next part we would use would be our derivative gain. So we've set our proportional, we've got good reaction, but we've got a little bit of hunting and overshoot, but not continuous hunting. What the idea of the derivative is to put the brakes on. So the derivative, as my previous webinar said, is more or less a duty cycle or position reaction to the rate of change of error. So it's the error speed that the derivative is looking at. So if we put in a little bit of derivative, you can sort of see, going from my first diagram to my second diagram, that we have, you know, reduced the amount of hunting. So effectively the derivative gain will be watching how quickly we are approaching our aim of 1200 RPM, and it will be slowly putting the brakes on, or reducing the duty cycle before we get to our aim, so that we don't overshoot it. So what you would do is you would slowly put in a little bit of gain derivative, a little bit more, a little bit more. Now obviously, just like brakes, if I put too much derivative in, I'm going to get my third diagram there, where you can see as the RPM is racing up, the derivative brakes early, as in too much derivative puts the brakes on too early, and I don't quite get there, and then the proportional takes over again and says, hey, no, we're not there yet, so add some proportional. As soon as that error starts to close up, the derivative puts the brakes on. So you get this sort of almost steppy response, where every time it wants to move from the proportional, the derivative wants to put the brakes on. So it means we've got too much derivative. So you'll be able to see this in your tuning. What we are looking for with our derivative gain is something a bit like this, where we want enough derivative gain where it's going to slow down our approach before we get there and before we have a chance to overshoot, but we don't want it so much that we get into this steppy response. So that diagram there would be classically a pretty good indication of what you're looking for. Now you will notice there is still a slight overshoot, but as I will talk about with sort of deadband later, this can be quite acceptable. So we've got the proportional to get us there as fast as possible without the hunting, and we've got the derivative just there to keep an overall eye on whether we do overshoot or not. But again, too much of either will either cause hunting or early braking. So sit there and you need to tune these things on the car. The other thing you will notice is, even though we've got there fairly quickly, we've had an ever so slight overshoot, after a while we still have what we would call a steady state error. So I want to be at 1200, but I'm actually only at 1120. So that means we've still got some little error that might be more of an annoyance than anything, but we reckon we've got our proportional and our derivative pretty good for response and, you know, lack of overshooting. So my next slide, what we can add in is some integral gain. Now again, from my previous webinar, the integral gain works based on how much time have we had an error for. So it's there to more or less clean up those last little bits of errors. So if we just, once we've got our proportional and our derivative gain sorted out, what we can do is then go in and put in a little bit of integral gain, and what you'll notice with my arrow there is that error that was there slowly over time, you know, just simply disappears. Now again, too much integral gain can cause hunting as well. So you don't want to just go putting in big numbers in big steps in any of these situations. You do want to take your time and do it in a sort of slow controlled process. Okay. Integral clamp. Again, please refer to my previous webinar for the term integral wind-up. But basically, with integral, we only want it to work over a fairly narrow band. So it's just there to get rid of the last little bits of error. So it should realistically only need a small range to work over. And just to give you a bit of an idea of how the integral band or integral clamps work, from our normal position we usually have a positive integral clamp and a negative integral clamp. So it just runs more or less a narrow window above and below the normal position, and in that window of duty cycle or position for the drive-by-wire, that's the bit, or that's the limits of the integral system itself. Maybe for boost control as an example, that might be plus or minus 5% of extra duty cycle, or, you know, reduction of duty cycle based purely on that last bit of steady state error. So we don't want these integral clamps to have too much range, because that can also cause problems with the integral wind-up. Deadband. Most of the PID functions will have a deadband as well. Now this is quite simply a close enough result. So as an example for my idle control there, if we said the deadband is 50 RPM, we are basically saying if my idle aim RPM in this example is 800, 850 is acceptable and 750 is acceptable. As a bit of a helpful hint, on idle control, the amount of deadband you have can depend on the number of cylinders and the type of engine. I usually would set the deadband based on what the engine sounds like. As a rough example, like a 4-cylinder engine, if you modify the RPM by 50 RPM, you can hear it and it sounds like it's hunting 200, but with say a V8 50 RPM you don't tend to notice as much. So this might be something that you would set specifically based on the engine and maybe how good an idle quality the customer would like. So same with boost control, you know, how much sort of fluctuation of boost is acceptable. If you set these that deadband too narrow, maybe like if you said 10 RPM, that means every time you go 810 or 790 RPM, the PID is going to try and calculate. So what you can have is a system which is constantly trying to calculate to a really small deadband, and then it can make the system, if the idle control is a little bit sensitive, you know, the idle can, you know, be basically the right RPM but still sound rough because it's constantly trying to change and get rid of a really small deadband. So, you know, in that case you sort of have to make the decision based on the idle quality you sort of want, or, you know, maybe is the boost, you know, is 5 kPa of boost, you know, nothing to worry about. Obviously you don't want to set it too high. If you set the idle RPM deadband at 100, that would mean 900 is acceptable and 700 is acceptable, and the idle quality wouldn't be any good either. Within the deadband, basically the PID stops and holds its current value. So it stops trying to update because you've said that it is within a band of RPM or boost that is quite acceptable. Okay, some helpful hints. This is probably more from my experience than any classical PID sort of tuning books, but you must understand what each number does. One of the things I find from doing support with customers over the years is that people don't generally understand what each of the terms do, the P, I and D, and maybe the feed forward. So they simply put in random combinations of numbers that don't really match each other and then get terrible results. You have to do this tuning basically in the steps that I've said in this webinar. So you start with your feed forward, then you do your P, then you do your D, and then you do your I last. So you need to sort of have an idea of when you're getting a certain type of reaction. You know, with a bit of experience you can sort of work out, you know, okay, is it the proportionals too much or the integrals too much? You need to understand what each number does, not just put in random combinations. Each gain component is continually being calculated and they can affect each other. So when I say, you know, there's the proportional, then the derivative, then the integral, they don't sort of happen, you know, one after the other. They're constantly being calculated and all working together. So what you might find is that when you set a proportional gain and then you get a derivative gain and they seem to match, you know, if you put in more derivative you might need to go back and change your proportional. So you're more or less getting your PI and D within a ballpark and then maybe trying some slightly different combinations to see if it improves the system. So as I said in the fourth point there, it can be an iterative process. You get your proportional right, and then once you get your derivative right, you sort of find that the proportional could possibly be a little bit higher or lower. So you might have to go through a couple of different combinations of numbers just to work out which ones work. Now, if you have an acceptable combination, just write down what your PI and D settings are. I find that some people might come up with a solution which is, it's 90% of the way there or quite acceptable, and then they think they'll improve it and then start messing around with the numbers and basically go the opposite way and end up with something that's back to terrible again, and then quite simply they've forgotten what their acceptable combination was. So once you get something that seems pretty good, just write it down or save the file as a separate file, just so you've got something to go back to if you continue on and sort of get to the point where you've gone backwards instead of forwards. Another thing that you should probably do is, if you read the help for the P, I and D terms in each of the different functions, you'll find that we generally give you a scaling which basically says the proportional term is 1% duty cycle for every 1% of error, or 1 kPa of error. So it gives you more or less a scaling, so you've got a rough idea of how the P, I and D are calculating ultimately the duty cycle. And if you're like me and you've got to test these systems, you'll do the data logging and then work out your error and calculate it by hand, just to check that the ECU is doing what it's supposed to do, and I can pretty much assure you it will be. It's fairly simple maths. And then experience. I wouldn't expect that anyone could watch these 2 webinars and then dive in and tune any PID control system. It does, like I said, take some experience to have an idea of, when you have a reaction that's maybe not a good one, what part of the system is, or part of the calculation is not correct or could be tuned better. Is it the P, I or D, or is it in fact the feed forward that you've had, maybe like the boat example where you need to add another axis into your feed forward just to get the control or the tunability that you want. Couple of things for idle control, PID specifically. Make sure your fuel table is consistent for any idle control valve position. So what I'm saying is, when the idle valve goes to a different duty cycle, which effectively opens up an airway, or the throttle body opens, just make sure that the engine doesn't go to an area on the fuel map that's either too rich or too lean. You want the fueling sort of consistent no matter what the idle valve is doing. Same with the ignition. Make sure that your ignition table is, generally you want it as flat as possible, so that you've got a more or less a consistent ignition timing no matter what the valve or the drive-by-wire is doing. Again, you want to make the system linear. If you've got an ignition table which has very sharp, steep sort of changes between 2 sites, well then extra timing produces more power, so therefore the linear reaction once the engine moves to that site on the ignition might not be so good. So remember, if this is an engine, it's fuel, air and spark. The PID is controlling the air. You have to make sure that the fuel and ignition match, otherwise the entire result is going to be terrible. And again, another thing people either don't do properly or completely forget about. Another thing, make sure the throttle butterfly or idle bypass screw is set so the engine idles slightly below the desired RPM, maybe at say 100 RPM below where you want it, with the idle control off. Okay, so we want to make sure that there's plenty of air, so that the thing doesn't stall if you're getting the PID sorted out and you haven't quite got there yet. There's nothing more annoying than an engine that simply dies every time the idle valve closes. So maybe set the base position for the butterfly or the idle bypass screw. Set that so that the engine is not likely to stall all the time while you are tuning it. Okay, if the engine does not idle well with the control off, don't try to fix it with the idle control. So one thing we always sort of tell people is, again, the whole theory of starting with an open loop system is, if this engine idles rough with the idle control turned off, the idle control system is only going to make it worse. I can't stress that enough because I deal with it almost weekly. But make sure, again, your fuel and your ignition tables, if the idle control is off, that engine should sit there and idle nicely when hot. If it's idling rough, you either need to fix that, or just accept that you won't be able to run idle control, because the idle control will just make that worse. So, an example of idle control on an engine with very large camshafts, like racing camshafts, is almost pointless, because the nature of the camshaft is going to mean that the engine idles rough anyway, so trying to put closed loop idle control on that is almost pointless. Another point for people who have stepper motor for idle control, the integral gain is not used, so make sure you set that to 0, because otherwise it will cause you problems. So that's mainly people with the earlier Holden V8s and earlier Evo Mitsubishis. So if you've got a stepper motor, integral gain is not used at all, make sure it is off. For boost control, and this is probably more based on my opinion than anything, but you can only control the boost once there is more manifold pressure than the wastegate spring will hold. So if you've got a 5-pound spring, that means you can't do any boost control until you've got more than 5 pounds of boost in the intake manifold, because you can't control it if if there's not enough boost to control the spring. So one thing I've seen before is when people are asking for a bar of boost at 3,000 RPM, where in a range where the turbo simply won't make that. What you can end up with is the integral wind-up, as we have discussed. More or less what's happening is the boost control system's been told to try and get a bar. It's physically impossible to do so, so it will wind its duty cycle up to the absolute maximum. So what happens as soon as the turbo does come on boost, we get a massive boost over spike, which can might make the car feel fast, but could also damage stuff if we're running fairly close to the maximum boost that the engine will produce, or maybe the ignition system, we might get a misfire. So just keep an eye on your maximum and minimum duty cycles, and maybe even your integral clamp tables. You want to make sure that that boost control doesn't wind up to its maximum duty cycle in an area where the engine simply isn't going to produce the boost requested anyway. I would sort of suggest maybe dropping the request boost to something more feasible. Again, you may need some restrictors in the system, in the vacuum lines to and from the boost control valve, just to make sure that the the controllable range of that valve is actually useful on the physical turbo system you have there. But there's a few more webinars by Pete Swinney if you want to know a bit more about tuning boost control specifically. Another thing I would sort of recommend is, with your maximum duty cycles, if you're let's say your duty cycle needed to get the boost you want is maybe 50% duty cycle, there's no real need for your maximum duty cycle table to be at, say, 80, because that gives you the boost control an extra 30% to work with, which is probably unnecessary. You just want a little bit of a ceiling of maybe 5 to 10% duty cycle above, just in case at some point you might want to add in a few kPa more boost or a few psi more boost. So don't bother giving the range of the system sort of too much headroom over and above what you actually need. So again, this comes into our normal positions and our minimum and maximum positions and checking our linearity. So all the open loop stuff we do in the back, or do to start with, again, very, very important. so don't forget it. Okay, thank you for attending my webinar. As always, these webinars are recorded and they will be put up on our website in the webinar section so that you can watch them later. Feel free to tell your friends and colleagues about them, and also if you have any other questions, generally we would hope you are members of our Motec forum by now, where you can post your questions and have them answered. There's generally always people around the world online, even if we've all gone home for the night. So thank you for attending, and I hope you can attend our future webinars.